Hi, my name is Stefan Hajnoczi, and I'm going to talk about optimizing KVM for NVMe drives. So what are NVMe drives? NVMe is a standard interface for solid-state disks. So it's a PCI storage controller interface, and there is an open specification and a standard Linux driver that can talk to any NVMe compliant device, and devices are made by multiple vendors. What's interesting about NVMe drives is that some of them have extremely good latency, much lower latencies than we've had in the past. So I quoted two figures here. One is for an enterprise SSD, so that would be something for data centers and servers and so on. This is an Intel Optane drive, and it's quoted at 10 microseconds for reads and writes. But even the consumer SSDs can be very low latency. So the Samsung 970 EVO Plus is quoted at around 17 microseconds write latency. Now, just because a drive says it's NVMe, just because it uses that standard doesn't necessarily mean it's one of these low latency drives. There are significant differences, so you should check the data sheet before purchasing drives. Now, in 2012, Jeff Dean published a slide that became very popular called Latency Numbers Every Programmer Should Know. And it's probably became popular because it's really interesting to see how long different operations in computer systems take. Now, the reason I'm showing this table and the reason it's interesting is because if you look at other storage, if you look at spinning disks, hard disks that have platters that store the data magnetically, and they have drive heads that need to move to the correct location in order to be able to read those blocks of data from the platter. Spinning disks have seek times. In order to perform random accesses, if we do the same random read, there's movement involved, and that takes time. So the time for that is quoted as 2 milliseconds. So comparing these two things, the hard disk versus an NVMe solid-state disk, we have 2,000 microseconds for accessing a random read and 10 microseconds. So there's a huge difference here, and you can see why optimizing for NVMe drives is very different than from traditional disks. So let's have a look at a relationship between IOPS and latency. This is an important one. In fact, this is the critical thing that drives the rest of this presentation and the optimization work that we're going to look into. It's the relationship between IOPS and latency. IOPS is the number of operations per second. And here I'm showing a simple model of doing one operation at a time. And the relationship is just the total runtime divided by the latency. That gives us the number of operations we can complete in that runtime. So the first thing you notice is that this relationship is non-linear, right? It's not just a straight line, it is a curve. And to start investigating it, imagine that we are at the right-hand side of this curve. We're at 20 microseconds latency. That means it takes us 20 microseconds to complete our operation. If we identify an optimization we could make to make the system faster, say it shaves off 2 microseconds, then we can bring it down to 18 microseconds latency. And the graph shows us how many IOPS we are going to get if we move it from 20 to 18 microseconds latency. Well, that slope is pretty flat over there at 20 microseconds. So actually the number of IOPS doesn't increase that much. But if you imagine for a second that we were at 4 microseconds of latency on the left-hand side of that graph, and then we shave off 2 microseconds. So again, here we're just shaving off 2 microseconds, the same adjustment in both cases. But now it brings us down to 2 microseconds, and we go from 250K IOPS to 500K IOPS. And this might be an obvious relationship because when we were at 20 microseconds and we removed 2, we only optimized away 10% of the total latency. But when we were at 4 and we went down to 2, we optimized away 50% of latency. So it does make sense that the jump is going to be bigger here because it is a bigger proportional improvement. But still, it leads to interesting things. First of all, think about having 2 independent optimizations, A and B, that you found and that you want to make. Well, one of the misleading things here is that if you apply optimization A, and then you apply optimization B, say both of them reduce the total latency by 2 microseconds, then if optimization A gains you 10K IOPS, optimization B will gain you more than 10K IOPS because it was applied afterwards, after we had already reduced the total latency. And because they're independent, if we do it the other order, the other way around, if we do optimization B first and then optimization A, then we'll have the reverse. Optimization B will give us 10 IOPS improvement, 10K IOPS improvement, and optimization B will give us more than that. So this can be misleading, right? It can be tricky. In the order in which we apply optimization, we can kind of fool ourselves thinking that one boosts IOPS by a lot and the other one doesn't. But in terms of total latency, it doesn't necessarily tell us how much time we've reduced. And that's why saying something like IOPS increased by 10K doesn't really convey enough information to know what is going on. You need to know at least the basic IOPS level you were at before in order to understand how the latency came into play. The other thing that's important about this graph is that NVMe drives being at 10 microseconds or less latency, if we focus on that, that is the left-hand side of this graph. That's where the graph becomes very nonlinear. That's where the slope gets very steep. So we need to keep that in mind, that any small change to latency, increasing it or reducing it on the left-hand side of the graph can have a big effect on IOPS. We need to re-examine the guest and the host software stack because the hardware is faster. So now we need to re-examine the guest and host software stack, and we need to rethink the architecture of QEMU, of KVM, and of the Linux drivers and so on, because the hardware has gotten so much faster. And when I say rethink the architecture, that's not a buzzword. What I mean by that is think back to that curve that we saw, the IOPS versus latency. The optimizations that we considered in the past and that had no measurable effect, they were not significant in the past, we decided they were too complex, or for whatever reason we didn't implement them in the past, those optimizations might now be relevant again, because even shaving off a little bit of time on the left-hand side of that curve can boost IOPS a lot and can allow the application to get better performance. So that's why I mean rethinking the architecture, because we really can reconsider things that didn't make sense in the past. And so that's the 10 microsecond challenge that we're going to talk about. Okay, so let's begin by looking at the IO request lifecycle. The IO request lifecycle is the core of what we need to understand in order to optimize this. Here is a high-level model. It doesn't show the specifics of virtualization, right? You don't see QEMU, you don't see KVM in here, or any emulated devices or the operating system or anything. This is just a high-level model. What it shows you is that an application that is running on the vCPU and decides to submit an IO request, in this case it's a read request that is being submitted, that request needs to be prepared, and then a message will be sent to the device notifying it that there's a request available, and then the device can process that request. Now, when that message has been sent, when we've submitted our IO, the vCPU might have no more work to do, or it might have some other tasks that it can run in the meantime while we're waiting for the request to finish. But either way, at this point, the critical path is in the hardware, because now the device, with its latency of, say, 10 microseconds, is going to be processing that request. And when it finishes, it sends back a completion notification to the vCPU. The vCPU is going to then process that completion and resume the application because the IO has finished. And so that's the life cycle of a single request, of just one request in isolation. And the important thing to understand here is that if we're trying to optimize the software layers, we need to study the mechanism through which requests are submitted, the mechanism through which requests are completed, and of course the code path and the layers of code that are parsing requests or creating them in memory and so on. Because that's what we can optimize. That's under our control. So you might have noticed that I've been mentioning latency all the time. And in this presentation, we are going to focus on latency. But latency is just one performance factor. There are others. So request parallelism is another thing that really boosts performance, and batching is one of the techniques to also benefit from that. What they can do is they can hide poor latency because you're able to do a lot of requests at once, and that way you're able to get a lot of work done even if the latency for one request is relatively long. But that's not what we're looking at here. The reason why we're looking purely at latency is because it's a fundamental thing, and if we optimize latency first, then we can consider those factors later. Now, there are latency-sensitive applications, and you can't hide poor latency from them. And the reason why is because they need a specific request to complete before they can continue. Even if there's a lot of parallelism available to them, because they need to wait for one specific request, they are bounded by the latency of that one request. And that's what we're trying to optimize here. And that's what's most obvious. Those types of applications suffer the most when they're run on virtualization on extremely fast hardware, because that's where the overheads become apparent. So what we're going to do is we're going to look at QDepth1 benchmarks, and that means only submitting one request at a time. We're also going to focus primarily on small block sizes. I will be showing graphs that have the larger block sizes just as a reference, but what we'll see is that other factors come into play there, that maybe the data transfer time and so on become more relevant, and they dominate, and we're seeing less of the completion and submission latency, which affects applications with small block sizes. And if you think about networking performance, a kind of analogy or similar thing there is benchmarking small packet sizes. That tends to show the cost, the per packet cost, and it's the same thing here. That's what we're focusing on. But you can get other perspectives. If latency isn't the only thing you're interested in, then take a look at these talks. There is another talk this year at KVM Forum, which investigates NVMe performance. And last year there was a great talk at KVM Forum that compared storage performance between hypervisors, NVMe, and various other things. Okay, now I mentioned that the mechanisms through which we complete and submit requests are important because they can determine the performance, or they can determine the latency. So let's have a look at the mechanisms that are used in Linux and in KVM today. These aren't the only mechanisms, but they're the main ones. First, there is eventfd, which is a counter, and it's a file descriptor. So when you read from this file descriptor, the counter is reset to 0. If it's already 0, then the read would block. Now, if the counter is incremented multiple times, you don't need to read it multiple times because a single read already resets it to 0. So what this means is that multiple notifications will be coalesced into a single read, which can be nice for performance. That helps. Now, because it's a file descriptor, it relies on the kernel scheduler to wake threads, because if you're trying to read from it, or you're in a select style system call waiting for that file descriptor to become ready, then your thread may be descheduled. Maybe the physical CPU will even be halted and put into a low power state. And waking up again from a halted CPU and resuming the application thread that may have been descheduled has some latency. And so this is not necessarily the lowest latency approach, the eventfd. But it is widely used. It's used by VFIO interrupts, by KVM's IO-eventfd and IRQ mechanism, and by Linux AIO and IOU rings completion mechanisms. So the other approach, polling or busy waiting, is also popular. So this simply means looping and continuously checking for the event that you're waiting for. Of course, if you do something from a tight loop, that consumes CPU cycles, and no other task can run while you're running. So it's not very power efficient. It does hog the CPU, but the advantage of this is when I mentioned how eventfd relies on the scheduler and the CPU could be halted and there's a latency associated with that. Well, polling does not have that problem, because when you're polling, you are running on the CPU. You have control. There is no latency. You're just going to read the completion value and see that the request is now ready. And so it has great latency. And that's why it's used. It's used by QEMU's AioContext, by KVM's iopoll and S, by CPU idle iopoll and Linux iopoll and DPDK and SPDK, all these things. They use it in different ways, in various flavors, but busy waiting is used in order to reduce latency. The reason I covered these mechanisms is because later on, when we look at the different optimizations available and the ones that I've tried out and that I'm presenting here, they are related to these on how to use them effectively. Okay, so the starting point for NVMe performance, for achieving good performance in VMs, is PCI device assignment. PCI device assignment is the way that achieves the highest performance. You can get bare metal performance by doing this. And the reason why this is so efficient is because when you take a PCI device and you pass it through to the guest, then the host is actually not involved in the critical path of processing I/O requests. This works because the PCI device, the hardware registers of the NVMe drive, will be memory mapped into the guest, so that accessing them doesn't require the hypervisor to be involved. And the IRQs, the interrupts that are raised by the NVMe drive, they can be directly injected into running guests if they are currently scheduled on a CPU, on a physical CPU. And that's thanks to posted interrupts, a CPU feature that's available on some CPUs. So again, there, the hypervisor doesn't need to have an interrupt handler. It doesn't need to forward that interrupt in the VM. Instead, the hardware is able to do that directly, which is good for latency. And then finally, for guest RAM access, the IOMMU, the IO Memory Management Unit, allows the physical PCI device, the NVMe drive, to directly access guest memory. So again, there you're also not involving a software layer in the hypervisor in order to perform any I/O. So that's why it's fast, and it's a great approach for high performance. It does have some limitations which cause it to not be as widely deployed as it would be great for performance, but it does not support live migration in most cases because that device is actually a black box to the hypervisor, and QEMU doesn't know about what's going on. It's unable to live migrate it because only the guest is using that device and has the driver and the state associated with it. Software features like backup and snapshots and so that QEMU can offer when you're using disk images are also not available, again because the hypervisor is bypassed. Another thing to consider is that exposing PCI devices to your guests may be inconvenient or may have security implications, and this is also why sometimes it cannot be used. The issue here is that, of course, if you have varying hardware and you want to live migrate your guests around, or if you just want to upgrade some of the hardware in your infrastructure, then the guests will actually see those changes. They will see the new hardware. So they need driver support and they might need reconfiguration if it's a different device that requires different setup. And so that can be prohibitive because in some environments you don't control the guests, they may be very old and so on, and so then you don't have the freedom to change the hardware. You might also be concerned about the guest being able to, say, do a firmware update on the device and so on. So there are some issues there with exposing those devices, so that's another thing to watch out for. And the final thing is simply the cost, because you do need to dedicate one PCI device to a particular guest. So other guests won't be able to use that same device. They cannot share it because only one guest can be the one that's running the driver at a time. Now, you can use SRIOV. Some devices allow you to virtualize them and split them up into virtual PCI devices, but that also has its limits. So here's the configuration. I'm not going to go into libvirt domain XML details in this presentation. I just want to show you the slides so that if you are watching this or reading this later on, you could have links to the documentation and find the keywords and things to look up in order to apply this configuration. Okay, so we've mentioned that for starters, PCI device assignment is the way to get good performance. You don't necessarily have the best performance right away with PCI device assignment unless you also consider the NUMA topology of your host. And what this means is that on modern systems, typically the system is divided into multiple domains that are called NUMA nodes. And a processor and memory and PCI devices are associated with a particular NUMA node. Accesses to the resources within that node are local and they are cheaper than accesses to resources in other nodes. And so for performance, it is important that we be aware of locality and we make sure that our operations are within a NUMA node where possible. So the tools that you can use to investigate this are NUMA CTL and LSTopo, and then you can get an overview of the topology of your machine. There are also performance counters that you can use if you suspect your application might be making cross-NUMA node memory accesses and so on. For more information, check out this talk that Dario is giving at KVM Forum this year about topology and NUMA. Okay, so in terms of how you set things up, libvirt has gives you the ability to pin vCPU threads to physical CPUs. You can also control QEMU's own threads, the IO threads and the emulator thread. They can be pinned to physical CPUs. In addition, you can control which host NUMA node to allocate portions of guest RAM for, and you can also expose a virtual NUMA topology. You can describe a NUMA topology that the guest will see. And the goal there is we want to align the guest's virtual NUMA topology with the host's NUMA topology. It should reflect what those resources on the host look like. And by doing that, the guest kernel, as well as NUMA-aware applications running inside the guest, will be able to make good scheduling and allocation decisions because they'll have that locality information. They'll know what is cheap and what is expensive, so they can choose the best configuration. Now here's a little example. This is trivial, but what's interesting is that it can also demonstrate how quickly we hit limitations and trade-offs here when we do NUMA tuning. So let's say we have a 1 vCPU guest, and what we want to do is we want this VM to do I/O. So we have an NVMe PCI adapter, and you can see the topology here in the diagram on the left side of the slide. Now, where should we put the vCPU? On which node should it run? Since it's going to be doing I/O and using the NVMe drive, let's place it on node 0, because that's where the NVMe drive is local, right? So instead of placing it on node 1 where it would have to cross the node, we put it on node 0. So that's the starting point. So let's pin the vCPU thread onto processor 0. Now, if we're using an IO thread in QEMU, which we will also get into later on, why using IO thread can be advantageous, that is going to be doing IO on behalf of the guest. And so that also needs to be where the NVMe PCI adapter is. And so we will pin it to processor 1. And of course, we're on node 0, so we want to be using RAM 0. So hopefully guest RAM fits into RAM 0's range. So there's enough memory there for our entire guest. That would be great. And that's the setup. But you can already start to see some of the challenges. What if we wanted a guest that had more RAM than was available in RAM 0? Then maybe we would have to define a virtual NUMA node and use some of the memory from RAM 1 as well. And hopefully the guest will then be able to make smart decisions about what to place into which of these two virtual NUMA nodes. Now, if we add more guests to this picture, it becomes even harder because at that point we need to maybe make sacrifices, decide whether to share resources like processors across guests or whether to assign vCPUs to processors that are on what is going to turn out to be the wrong node. Now, today, NUMA tuning is something that pays off for performance-critical VMs. Doing this manually pays off. And hopefully in the future, we'll see more automatic NUMA tuning support in the management tools that use KVM so that they can automatically set these things up and we don't need to manually tune it. It gets especially hard when we have a lot of VMs or when we do live migration, so the situation is dynamic and it's no longer so easy to come up with a static pinning that makes sense. Okay, so we covered the importance of NUMA and a bit about how to tune it and where to look. So next up is CPU idle halt poll. This is going back to the IO request lifecycle that we looked at. So what we saw was that the two important mechanisms that we have are submitting requests and completing them. Well, if you have passed through an NVMe PCI device, there are interrupts for the completion. When requests complete, there is an interrupt. Now, halting a vCPU involves a vmexit, and if there's no further work to do even on the host, then maybe the physical CPU will halt too. It will go into low power state, and then when the NVMe drive completes the request, it will fire the interrupt, the CPU will come out of that low power state, and there's a latency cost associated with that, and then we can re-enter that vCPU, can VM enter, and you can see that this becomes a chain of several steps, and it has a latency cost, so we want to avoid that. What the CPU idle halt poll driver does is it runs a busy wait loop inside the guest, so on that vCPU, at the point where it decides, oh, I have no more work to do. So it has a timeout, and it says, well, I'm going to try running a busy wait loop for a little while at least to see if something still becomes schedulable and becomes ready to run. And so that way, the vCPU is actually running, is actually active when that interrupt comes in. And so when that interrupt is delivered, we can quickly schedule the application again after completing the request, and we don't need to go through this long path of going down all the way to a halted physical CPU and coming back out. That decreases latency. Now this mechanism makes sense when you are pinning vCPUs, because when you're polling, you're wasting those CPU cycles until there's some work to do. And of course, if you had lots of VMs and if they were sharing CPUs, you wouldn't want them all to poll. So this is something to do when you have a high performance or performance critical VM and you have assigned it a dedicated CPU. Okay, now here's the tuning. This is just for the syntax. I won't go into detail. All right, so now here's our first graph. So these are the results for doing random reads and random writes, QDEP1, on an NVMe drive. And what we see here is the blue bar, the leftmost one, is the bare metal result with the NVMe drive. The red bar, the one in the middle, is the VFIO result. So that is a virtual machine with a PCI device assigned to it. And we can see that that's typically lower. Not in all cases, but it's often lower, and even by a significant amount. And then the final result is the VFIO with that CPU idle halt poll driver enabled. And you can see that that one performs very well. Why is it performing better than bare metal, right? How is that possible? Well, it's because bare metal isn't doing polling. And so bare metal might halt the CPU. It will save more power, but then it will also have higher latency. And the VM is staying active, the CPU is still running, and so it's able to take those completion interrupts with lower latency. So actually in this benchmark it achieves higher performance. So that's what we see here. And we're going to take this a step further. There's another polling approach we can use, and that will actually make the bare metal versus virtual machines comparison fairer, and it will show us the final picture. So here we go. The Linux NVMe driver allows you to allocate queues for specific usage. So it's possible to actually reserve polling queues. And what those poll mode queues do is when an application sets the high priority request flag, then the kernel will busy wait for those requests to finish. And it just calls the poll function in that driver, in the NVMe driver. And that function will just check. It will just check memory and have a look to see if the request has completed yet. So the kernel can do polling for us, and this is called iopoll. And so this improves completion latency, and actually more than CPU idle halt poll, because here we're guaranteed to be spinning and it doesn't give up. It keeps running in its default mode at least. And this allows us to make a fair comparison, because this is done by the driver in both bare metal and in the virtual machine case. So at the bottom of this slide, here's the syntax in case you want to see how to enable it. And let's look at the performance numbers. So as you can see on this graph, at this point, when we enable that feature, first of all, the absolute number of IOPS, the number of I/O operations per second that we can achieve, have jumped. The max we were at was around 80K before we used iopoll. Now that we're polling all the time, we get up to over 120K IOPS for queue depth 1, 4 kilobyte requests. So you can see that that's a significant performance improvement enabling iopoll. The other thing we see here is that the gap between bare metal and VMs has closed. So at this point, they're very similar. And you can say that using PCI device pass-through, you can get bare metal performance. So that's great. But what about situations where you cannot use PCI device assignment, right? I had this big disclaimer. I covered all the cons of why you sometimes cannot use it. Well, in that case, you can use VirtIO block. And VirtIO block is an emulated storage controller. It's a para-virtualized device that was designed specifically for virtualization, so it's been optimized over the years and has evolved. And so it's a good storage controller to choose if you want to get good performance with KVM. There are two settings, though, that I want to discuss here because they're not enabled by default yet, and they do boost performance, so they're worth considering. The first one is multi-queue. Although the feature has been there for years, it hasn't really been used. And in QEMU 5.2, that's going to change. In QEMU 5.2, the number of queues is going to default to the number of vCPUs. In other words, multi-queue will be enabled by default on VirtIO block and also on VirtIO SCSI devices. The reason why this is a win, the reason why this improves performance, is because giving every CPU, every vCPU, a dedicated queue means that now the completion interrupts, they can be directed at the CPU that submitted the I/O. And that's the one where the task is scheduled and where we want to do our completion. We don't want that interrupt to go to some other vCPU that then says, oh, okay, I'd better wake up that task that's ready to run on another CPU and I'll send a message. We don't want interprocessor interrupts. So by giving every vCPU its own queue, we can eliminate that and we can improve interrupt completion latency. So that's why multi-queue helps. In addition to this, the Linux block layer also has multi-queue support, and there are some code paths in the Linux block layer that take advantage of it. When the driver only allocates one queue, we don't take those code paths. And the most obvious user visible effect of this, for example, is that the I/O scheduler is different for devices that have more than one queue and that are multi-queue block drivers. So that affects latency too. And so it's best to enable multi-queue. Next, there's the VirtIO 1.1 packed virtqueue layout. So this is a new memory layout for the queues that VirtIO devices use. And this layout is more efficient. In the benchmarks that I've run, I've seen that it improves VirtIO block performance. So this is also worth taking into account. It's not a huge win, but it is a small win. And when devices are so low latency, then every small win is worth taking. Okay, now here's the syntax. We'll move on. And what we're going to do is I'll walk through several more configuration topics, and then I'll walk through some optimizations that I've implemented, some prototypes, some new stuff. And finally, at the end, we'll look at a graph that stacks them all up, and we can see how incrementally, by combining them, we can increase IOPS significantly. So here we are. IO threads is the next feature. If you're using VirtIO block, that is critical. IO threads are a way for defining threads and assigning devices to them. So it gives users control over which physical CPU, device emulation, and IO will run on. So there's an n-to-1 mapping there. You can assign multiple devices to a single IO thread, and you can define multiple IO threads as well. So it gives you a lot of flexibility, and this is great because it allows us to reflect the NUMA topology in our system. It is also good for scalability, because when you have VMs with many devices that are doing heavy I/O, you may want to put them into separate I/O threads and run them on separate CPUs so that there's enough resources for both of them and no interference between them. The final thing I want to mention about I/O threads is that the I/O threads feature, when it's enabled, that device will be able to take advantage of an adaptive polling event loop in QEMU. It's a different code path from QEMU's main loop, and it has lower latency because it's able to do polling instead of always yielding when it waits for file descriptors to become ready. So that's another reason why it's faster. And we'll see the numbers later on when I show the graphs. So here's the configuration, the things you can do for defining I/O threads, pinning them on the host, and then assigning devices to I/O threads in libvirt XML syntax. Okay, so now we're going to move on to things that aren't as standard yet, things that aren't as widely known and as widely used. There has been a Userspace NVMe driver in QEMU for some time now. It's been there for a long time, but it hasn't been used very widely yet. What it is it's somewhat similar to PCI device assignment in that that PCI device, that NVMe drive, can be assigned to a particular VM. However, instead of passing the device through into the guest and exposing that physical device to the guest, we still have an emulated VirtIO block device that the guest uses and sees. And in QEMU, we have the driver. So it's in QEMU Userspace in the host, and it's an NVMe driver. And so what this means is that we're able to get some performance benefits from having a Userspace driver that bypasses the kernel. That means no system calls are necessary, and there is a shorter code path that's completely under the control of QEMU, while still offering QEMU's block layer features, things like live migration or snapshots and so on. Even image formats can work on top of the Userspace driver. So this solves some of the limitations of PCI device pass-through. And right now, some improvements are being made upstream, and activity has started up again around this driver. Non-x86 architecture support is being added, multi-queue is being added, and more. So this is the syntax for configuring it. One thing that is missing from the NVMe Userspace driver in QEMU that I wanted to add, an optimization I wanted to try out, is polled queues. Because in NVMe, when you create a queue, you assign to it an interrupt. The completion queue has an interrupt, and you can turn that off completely while creating the queue. And when you have a queue that doesn't have an interrupt, you can just poll for completions. You can just look at the memory and see when those requests become ready. And so doing so is an alternative to interrupts. Effectively, this is kind of like switching from the eventfd style mechanism to a polling mechanism. And so we hope that it will reduce latency. One interesting thing about doing this, though, was that it requires changes to QEMU's event loop itself, because QEMU's event loop is really fundamentally designed for file descriptor monitoring. The adaptive polling has been added to it, but the whole premise is that we only poll for short amounts of time. Now, when we have a poll mode queue in the NVMe driver, we need to poll all the time. But if we poll all the time, we will be starving the file descriptors, right? Because we're just spinning in our busy loop, but we're not looking at the file descriptors. So I have some patches that I'm going to send upstream that extend the event loop. And in fact, some of the IOU ring work has already gone upstream. And I found that using IOU ring, we're able to do this efficiently and integrate it into the busy wait loop without using syscalls. Okay, so we'll look at the numbers for that in the end. The next thing I want to share is an idea that in one form or another has already been around for a long time. In 2014, when we introduced coroutines into the core block layer and started using them for request processing, that was very useful because we needed them for things like I/O throttling and some of the operations that were just getting really, really complex and difficult to write in an asynchronous style. So now there's request queuing and so on in the core block layer in QEMU. But there was concerns even back then that maybe this overhead will become a problem. And so there have been discussions in the past about can we optimize it away. And really the thing is, when you are not using certain QEMU features like disk image formats or IO throttling or storage migration, while those things are inactive, you don't really need to do the full request processing. All that machinery, that infrastructure is only needed to support those features. So wouldn't it be great if there was a way to bypass it when it's not needed? So as a prototype, I've tried implementing this. I've tried implementing an AIO fast path. What it does is it introduces an AIO interface to the block drivers in QEMU, because currently they have a coroutine interface, which kind of assumes that you're in this full request processing mode. And that allows the VirtIO block emulation to call the NVMe Userspace driver with relatively little overhead, and we can skip the full request processing step. So we'll see those numbers. The next thing I want to mention is that when we looked at PCI device assignment, we saw how beneficial Linux iopoll is. We saw that polling for the requests from the NVMe driver it reduces latency, and it got us the highest IOPS that we've achieved so far. We had this 120K IOPS bare metal. So VirtIO block today, the guest driver for VirtIO block does not implement this interface yet, but it's a driver interface, and in fact it's this one function that we need to implement. And so I have also written a prototype for that. It only supports QDepth1 because that's what I was benchmarking. It's not a full implementation, it's a prototype to check what kind of effect it has on performance, and the link to the Git branches is on this slide. So we'll look at that. Here we are. So this is the final incremental applying all of these optimizations on top of each other and how far it gets us. On the left-hand side, the starting position, we want to look at bare metal. And without iopoll, bare metal is at 78K IOPS. Now, when we configure QEMU with a file AIO equals native, so this is a standard non-optimized setup, and we don't use the IO thread, then we start at 21K IOPS. So that's extremely low. We can see there's a lot of overhead. I wouldn't necessarily say that this is what most QEMU users experience today, because IO threads is recommended, and more of the management tools built on top of KVM and QEMU have been using it by default. So hopefully most users today are around the second blue bar, the IO thread bar. So when we add IO threads, then we are at around 46K IOPS. There's still significant overhead, right? It's still pretty bad. So next up, we can enable VirtIO block multi-queue. Now, doing it at this stage actually turned out not to be very instructive. Although it slightly improved performance, it wasn't very significant in this graph, but it's still essential. Part of the reason why it didn't improve performance very much in this graph is because I was already using pinning both inside the guest and on the host and so on. So everything was already set up optimally. Adding the queues didn't help. The IO scheduler was already none, so that didn't help, and so on. But it is an essential part of making things scale and making things work. So we keep multi-queue. Next up, we introduce the Userspace NVMe driver in QEMU, and that boosts performance. So we jump almost 10K from 46K to 55K. So that's a nice boost, getting us closer to bare metal. Now what happens when we try the VirtIO block guest drivers iopoll prototype? So adding that on brings us up to above the initial bare metal number that we collected without iopoll on the host side. So what this is doing is, now that we're polling and we're using more CPU cycles, we are able to make some ground there. We're able to reduce the latency that we had. So this is looking good, but it's also unfair, because now really we should be comparing against a bare metal that is also using iopoll. So let's do that. On the right hand side of the graph, you see the gray bar. That is 120K IOPS. That's bare metal with NVMe iopoll. So we're still behind, we still have overhead, but our absolute number of IOPS has increased quite well, and we're not done yet. So next up, we can try the NVMe Userspace drivers polling queues, where we are polling in QEMU in the IO thread, and this brings us up to 94K IOPS. So that's definitely a worthwhile improvement, a nice jump there. And then finally, the AIO fast path that I just mentioned. So this is the final optimization that I'm going to show today, the final prototype that I wanted to share. And that bypasses the full request processing in QEMU. And as you can see, so that is another 10K further towards closing the gap to bare metal. So that's the status. That's what I wanted to share with you. And I'm working on upstreaming these optimizations so that they can be used. But the entire VirtIO block and NVMe approach with the NVMe driver, NVMe Userspace driver, has still left us with a similar limitation as PCI pass-through. We still need one device per guest. Luckily, this year, a new tool has been added to QEMU called QEMU Storage Daemon. And this is a separate program that has QEMU storage-related functionality. In addition to that, a vhost user block server has also been added to QEMU, which is very convenient. It means that now we can use the storage daemon, we can host the NVMe Userspace driver inside it, and that one daemon can serve multiple guests. So we now have the ability to share a single PCI device and use the Userspace driver and have multiple guests. So that solves that limitation. It's already available in QEMU.git, but the code path is different from the VirtIO block results that I presented to you. So those optimizations don't apply yet. Some of them still need to be ported to this. So over time, we can expect this to equal the results that I just showed. And then this will be an excellent way for if you need to share drives. On top of this, the QEMU storage daemon offers a lot of other functionality. Some of the cool things are NBD exports that would allow you to also attach those drives on the host, or applications can use them. And fuse exports are also in development. The block jobs features are available. So QEMU storage daemon will be a nice utility, and I think we're going to see more use of it in the future. Okay. Now, if you saw the QEMU storage daemon slide, you might have thought, wait a second, this is a familiar architecture. We know this approach. Yes, it's very similar to SPDK, Storage Performance Development Kit. And that also uses a polling architecture, and it's been around for years. In fact, the vhost user block interface was created in order to connect QEMU and SPDK. So we're very thankful that that already exists and we can reuse it. So I wanted to mention SPDK because obviously this has some influence and it's a great project to check out. If you want to find out more about what's going on in improving the general non-NVMe case, please check out Stefano Gazzarella's talk this year at KVM Forum. He'll be going into what he's done with IOUring and some of the new stuff that he's working on. Finally, the future direction. So in the short term, it's time to get these prototypes into a polished state, get them upstream. That will allow us to reach the performance that I've shown you here on these slides. And in the longer term, I think what's clear is that PCI device assignment, because it gives this bare metal performance, it's important to find more ways to pass through devices, because when the hypervisor is not involved, when there's no software path, that's how we get the best performance. So, summary. What have we looked at? Well, there's the basic configuration and tuning that is essential, the NUMA, CPU idle iopoll, and IO thread setup. That gives you a basic performant starting point. And then you have the big choice. Do you want to use PCI device assignment? Because that way you'll have the minimal overhead. That's the best way to go if performance is critical. But you need to keep in mind the limitations of that feature. And if you decide that you can't use PCI device assignment, then you can use VirtIO block with the Userspace NVMe driver. That will boost performance. And finally, the QEMU storage daemon now allows the sharing of Userspace NVMe drives with multiple guests. Thank you. I also published the Ansible playbooks that I used to collect the data if you want to go and look at the specifics of the benchmarks. There's a URL in the slide. Thank you very much.